Hey Randy, this is Chris back again, and I thought I'd do a real quick, or maybe not real quick. We'll see how it goes. But on the last video, I talked about the concept of enthalpy and how we can measure enthalpy as far as energy loss or energy gain. And enthalpy was symbolized by H, and we knew that a negative delta H. Okay, a negative delta H tells us that the chemical reaction released energy, so there was an energy loss, and that was exothermic, whereas a positive delta H means that energy had to move in. There was an energy gain. Energy was taken from the environment, and that tells us that we're talking about an endothermic reaction. Um, and enthalpy is kind of a component of a broader field of study known as thermodynamics. Thermodynamics. That's kind of a mouthful, but you've heard of this word before. And thermodynamics is really looking at the conversion of energy and the flow of heat. Heat actually being a sort of a form of energy. And we talked about energy a little bit in the last video, and we defined what energy was. And let's just be clear that there are a couple of major types of energy, broad types. You have what's known as kinetic. You have kinetic energy, and then you have potential. Okay, you have kinetic and potential, and kinetic is the energy of movement. So if you have something it's really hot, for example, it has a really high temperature, then we know that the energy of the molecules, the kinetic energy of the molecules, or the average kinetic energy, is really high, and those molecules or atoms are vibrating back and forth very, very rapidly. That's what gives something its temperature. We know if something's moving very fast, it has a certain amount of kinetic energy, and so on and so forth. Potential energy is a form of stored energy. So it's an energy that's stored up, and potential energy is really important because we see this in chemical bonds, and when chemical bonds are broken, like when you break the H2 bond, the energy, the potential energy that's stored in those bonds can then be transformed into heat, and that can be released, and we measure that as a negative delta H. Okay, so thermodynamics is certainly going to be very important, play an important role in chemical reactions. And when we talk about the thermodynamics of chemical reactions, there are what we call these variables of state, or sometimes these are called state variables. And these look at the state of a system, and a system is just basically what we're looking at. So a chemical reaction could be a system, and these look at the big picture. Okay, these are big picture variables. Okay, and they don't really rely on the process so much. And what I mean by that is if I have some sort of chemical reaction, and let's say it starts here, is activation energy, it goes down. Okay, a state variable doesn't depend on the pathway that this chemical reaction traveled. A state variable is just, okay, it tells you what state the system is in here and what state the system is in here. And these include things like pressure. These include things like volume. These include concepts like temperature, pressure, volume, and temperature. But there are also some other state variables that deal with the energy. They deal with the energy, the amount of disorder in my system and how stable the system is. And these fundamentally, these are not pressure, volume, or temperature. Okay, even though pressure, volume, temperature are state variables, these variables are very different, and they really go back to the laws of thermodynamics. The laws of thermodynamics are kind of these concepts, these state variables fall out of that. And so the first law of thermodynamics tells us that energy is not, it's not created or destroyed. Okay, we can't pull it out of our butt. We can't create it or destroy it. We can just transfer. We can transfer and transform. So we could transfer and transform energy into different forms. And so when we talk about measuring energy and measuring how energy is transformed and where energy goes, okay, where energy is going, okay, the first law of thermodynamics, that's the concept of H, or enthalpy, okay? Enthalpy is just really looking at is the energy. So here I have my chemical reaction occurring. Is energy leaving the chemical reaction? That would be a negative delta H, okay? Or is energy going into the chemical reaction from the surroundings, and that would be a positive delta H, okay? So you're not making or you're not creating or destroying energy, you're just, it's either moving in or moving out, and that's really what enthalpy looks at. And then the other concept is a measure, it's a measure of disorder. Some people may be much more eloquent in the way they describe this concept, and certainly when talking about information theory and quantum theories, this concept it really has to deal with information and how much information you need to know about the state of a system and that. But for our purposes, look at it as a measure of disorder. And this concept is known as entropy, E-N-T-R-O-P-Y. It's not enthalpy, it's entropy. And entropy is often symbolized as S. So a change in entropy would be delta S, okay? And this goes back to the second law of thermodynamics, which says that the entropy, okay, the entropy in a system, a closed system, will tend to increase over time, okay? So a system where I am not putting energy into it, the system is I just have a system sitting all by itself, that system, the amount of disorder within that system will tend to increase. So I think of it like this. Let's say that I have a cup of water here, and this to say this is time 0, okay? And I have a drop of food coloring in that water, okay? And then I have this system, and let's say that I have isolated it, okay? It is isolated, okay, from, I'm just looking at this particular part of the universe, completely isolated, so it has a certain amount of internal energy and heat and all that. It is completely isolated. I put a little drop of food coloring in. What is going to happen if I look at that system, okay, and I observe that system at, let's say, 100 seconds later? Well, what we see happening is the little molecules that make up that, okay, that drop of food coloring, they're going to diffuse out, right? So is this more or less disordered than this? Well, clearly this has more disorder. Okay, this is more disorder here. These molecules are spread out more. So this is more disordered than this here, where the molecules are closer together and better arranged. So you would say that there has been a positive delta S, and that's what's meant by the second law of thermodynamics. If you let a system kind of stay by itself and you don't intervene, there will be a tendency, a movement toward disorder. And that movement toward disorder is what we call entropy. Just like if I have let's say, maybe a container with gas molecules, and I arrange all the gas molecules on one side of this container. Okay, this is a low entropy, low entropy setup here, right? Because this is highly ordered. What do you know is going to happen to those gas molecules if you let the system evolve? Well, they're going to diffuse out, right? They're going to go everywhere. They're going to diffuse throughout this container, and it is going to go, and it'll end up in a situation like this where I have a high entropy system. Okay, so that's what measuring entropy is. So when we talk about a chemical reaction, not only do we want to know what's happening to the energy, okay, so here is the energy, okay, and typically for spontaneous reactions that happen spontaneously, that is, once you get over the activation energy barrier, tend to have negative delta H's. So they tend to have negative enthalpy. Okay, so this is energy time. But let's now graph, instead of energy, let's graph entropy versus time. And what do you think is going to happen? What is a spontaneous reaction that's going to be more spontaneous? Is it going to have negative or positive entropy? Well, the second law of thermodynamics says that a reaction is going to proceed more spontaneously if the delta S, the change in entropy, is positive, if it increases. So if I have a chemical reaction where the entropy is here at the beginning of the chemical reaction, and then at the end of the chemical reaction the entropy is here, okay, I have had an increase in the entropy, okay, in the entropy, okay, that has increased. So this is going to be more spontaneous in nature, okay, more spontaneous in nature. And then the last concept I want to talk about kind of combines, is kind of a combination of H and S, okay? And that concept is known as Gibbs free energy. Gibbs free energy. And Gibbs free energy is a measure of stability, or instability. And remember, we said that in a chemical reaction, typically when I have an exothermic reaction like this, okay, because there's less energy here, okay, the products have less energy, okay, there has been a negative delta H, okay, they have lost energy, their enthalpy is negative. And remember, in nature we said that the more negative, okay, the lower energy equals higher stability. So in an exothermic reaction, I am going to have higher stability if my products are at lower energies, okay? They are more stable. They're not going to want to react as much as if I ended up at higher energies. And that's what the Gibbs free energy is looking at the stability or the instability of what's going on. And if we want to kind of look at calculating the Gibbs free energy, or the change in Gibbs free energy, that is delta G, okay? Delta G equals a change in enthalpy, so whatever my delta H is, minus the temperature of the system multiplied by the change in entropy, okay? And let's just throw this in the back of our minds here, okay? So, when we look at our Gibbs free energy, what do you think is going on here? Well, a lower delta G's correspond with what? Well, there's lower Gibbs free energy when the reaction's over with. What does that mean? Well, that means that my products are more stable. Okay? A higher delta G means that the products are less stable. Okay? Are less stable. So let's clear this. Let me put this up here again. So the Gibbs free energy, the change in Gibbs free energy, is equivalent to the change in enthalpy, subtract the temperature, okay, multiplied by the change in entropy. So let's say that I have a chemical reaction. Okay, I have an exothermic chemical reaction. All right, maybe the combustion of hydrogen. So I start here, I get over my activation energy, and I'm down here. Okay. And let's just say we're going to kind of hold temperature constant, okay? We know that temperature is going to change, so I'm just going to kind of hold it constant and just look at delta S and delta H. Okay, so the change in Gibbs is going to equal, let's say that the delta H, the change in enthalpy, is a negative 10 units. Okay, it's negative, so that's exothermic. And then I'm going to subtract, okay, and let's just say that the temperature is maybe 100 Kelvin, and my change in entropy, let's say that the delta S is, I don't know, plus 10, okay? So my entropy is higher. The entropy of the products is higher than the entropy of the reactants. Okay, fair enough. That looks good. So it's more disordered, and I have lost some energy. So what's going to happen here? Let's just calculate delta G. Well, delta G is going to equal 100 times 10. Well, that's just 1,000. So what's negative 10 subtract 1,000? Well, that's negative 1010. Okay, so my delta G, my Gibbs free energy, is very, very negative when this is all said and done. What does that mean? That means that at the end of the reaction, this is very stable. It's a very stable situation. So that favors, okay, that favors a reaction that's going to be spontaneous. So at the end of the day, what we can say is if a chemical reaction is going to be spontaneous, what do we like to see? Well, we like to see negative delta H, okay? We like to see negative delta H, we like to see positive delta S, and we like to see what kind of Gibbs free energy? We like to see lower delta G's, okay? That's a spontaneous. For a non-spontaneous chemical reaction, okay, so this is a chemical reaction that doesn't particularly want to react by itself. So that means that you have to intervene, and you have to add energy, and you have to add enzymes, and you have to actually work really hard to get that chemical reaction to occur. It's going to have a positive delta H, okay? It is going to have a negative delta S potentially, okay? You may be taking like let's say like water, and I want to freeze that water, so the liquid water has higher entropy than the frozen water, well, I'm going to have to expend energy to decrease that entropy, right? That's not necessarily a spontaneous thing without me, doing something to the environment, and I'm going to have a positive delta G. Now, where this can get kind of weird is, do you remember the little ice pack? The little ice pack analogy that we talked about a little earlier. I'll just kind of run through this, and then I'll go ahead and cut the video off so it's not so incredibly long that it's just crazy. But you remember the ice pack? We talked a little bit about that, and the ice pack contained ammonium nitrate, which is NH4NO3 in its solid state. And we said that plus H2O, and I had a chemical reaction where it split, okay? So there's NH4 plus aqueous, and that gave us NO3 negative aqueous, okay? And we said that the delta H here, okay, the delta H was positive. So if we just look at the change in enthalpy, we would say that this is a non-spontaneous reaction, right? You'd say, well, this is probably not going to occur spontaneously, yet we do see it occur spontaneously. At least we see it occur spontaneously at sufficiently high enough temperatures, okay, at room temperature. I'll give you that. So what's going on here? How can this still proceed spontaneously? Well, what happens is, if you notice, the ammonium nitrate here, this polyatomic ion, this molecule, is one molecule, right? But over here I have one and two. I'm breaking these molecules down into this. So what is happening to entropy, to the entropy of the system, okay, the delta S? Well, the delta S is positive. My entropy is increasing, and that tends to be more spontaneous. And we said that at the end of the day, spontaneous versus non-spontaneous, it's going to be delta G, right? And you remember the formula for delta G? So let's just kind of pull that formula back up real quick. So delta G equals the change in enthalpy, subtract the temperature, multiplied by the change in entropy. So change in enthalpy minus the temperature multiplied by change in entropy. So even though my delta H is positive, if my temperature, okay, my temperature is sufficiently high enough and my change in entropy is sufficiently high enough, okay, the temperature and the change in entropy alone can make a reaction that has a positive delta H spontaneous. It can make the overall reaction spontaneous. Whoops. It can make the overall reaction spontaneous because the temperature is sufficiently high enough and my change in entropy favors the chemical reaction to occur spontaneously, and my overall delta G will be negative. So I know that's kind of complicated, and I'm not going to make you do any of these calculations or anything like that, but I just want to see how looking at the concepts of thermodynamics can really help us understand how certain chemical reactions are going to proceed. Okay, take care.